My name is Nanus Rachel. Me and my colleague Alinda Tracy shall take you through multi-class classification as a subtopic under machine learning. We want to understand how multi-classification can be used, when and how, and why. First of all, we have to understand what multi-classification is. Multi-classification is a type of supervised machine learning where a model is trained to classify data into more than 3 categories. Here we have two basic terms. Here we have supervised machine learning, and we all know that in supervised machine learning we are using labeled data. Let's say you have 3 classes of animals. You have a cat, you have a dog, and an elephant. So you want to train your supervised machine learning model by showing it thousands of pictures of these 3 classes. So in the long term, it will learn the pattern. Then when you bring in a new picture or a new image of the animal, it can classify that this one belongs to this one and this one belongs. So it is using a labeled data like the images of the animals. So unlike the binary classification where there are only 2 class instances, in multi-classification we have more than 3 class instances. So first of all, we want to understand how does multi-class classification work. First of all, we all know that when you're training a machine learning model, the first thing you do is to collect data. You need to have a data set. So let's say you are classifying brain data. You're classifying maybe like in our project we are classifying dementia diseases, and we want to collect brain waves from the participants suffering from each of the diseases, from each of the types of the dementia, and then from the healthy individuals as well. So we will go and then scan the brains, and then we get the brain signal waves. So that is the data we are going to be using. So then you have gathered your data. So you want to clean your data and to remove the noise. So you work with the cleaned data, and then now you have cleaned your data. Like some data sets have so many features, and this makes them to have high dimensional, to be high dimensional. So meaning they are hard to visualize. So you want to reduce on the number of features, or you want to reduce on the dimensionality. You have to apply some techniques to extract out the most important features while ignoring the less important ones. So after you have extracted out the most important features from the dataset you're using, you want to choose which multi-class model to use. You can either go for the machine learning models like the support vector machine, or a deep learning model, depending on the data depending on the classes you have. If they have maybe they are too similar, like they are too similar, then you have to apply a deep learning model here. So after you have chosen your multi-class model, you want to train your model using the data set you have. So in the long term or with time, this machine learning or any multi-class model you're using will learn the patterns in the data feeding it or you're using to teach it, and then it will learn to classify. No, it will learn to recognize the difference between the data, then it will learn to classify between the groups. Let's say it will learn to classify that this green signal wave belongs to Alzheimer's disease, or it belongs to frontotemporal dementia, or it belongs to the healthy subjects. Then, when we want to maybe want to test to see if our model has learned the pattern or it is ready for work, we want to make predictions, then we give it new data. Let's say you give it new brain signal data, and then it will decide to which group it belongs to. Then you're there asking, why is multiclassification important? Multiclassification is important in real-world applications like medical diagnosis. Let's say now, like our project, we want to classify brain diseases like Alzheimer's disease, the frontotemporal dementia, or the normal cognitive functions. Or maybe you have 3 classes of diseases and you want to classify. You want to distinguish between them at the early stage, because we may find that these 3 classes of diseases have similar symptoms, so it makes it hard to tell apart. So you have to apply multi-class classification for this now. And multi-classification can also be used for image recognitions. Like I said earlier, you have 3 classes of animals, then you're using images of these animals to train your machine. So depending, maybe when you get maybe another new image, this machine can be able to tell the difference, and then it can classify to which of the 3 classes that image belongs to. Then multi-class classification can also be used for text and speech classification. And there are methods to use when you're training a machine to classify data into multiple classes. We have 1 versus all and 1 versus 1. So, and the number of the classifier models depends on the technique you're using, basically. Yeah. First, I'm going to discuss 1 versus all. So, in 1 versus all classification, for n class instances in your data set, we want to generate n binary classifier models. So, for example, our data set has 3 classes, have the Alzheimer's disease, frontotemporal dementia, and then the healthy participants. Now, for 1 versus all, let's say you have 3 class instances in your data set, so you have to create 3 binary classifiers. What I mean is that the number of the classes in your data set has to actually be the same as the number of the binary classifier models. So we have 3 classes, so we are creating 3 binary classifier models. So each class distinguishes 1 class from the rest. So each classifier distinguishes 1 class from the rest. So this is now our main data set with the 3 classes: the Alzheimer's disease, the frontotemporal dementia, and the healthy individuals. So we create 3 So we create three classifier models. One is for classifying frontotemporal dementia. The other one for Alzheimer's disease, and then the last one is for the healthy subjects. So now we have created our classifier models. We want to create a training data set for each class. So, like for the other one, we are using the brain signal. We are using the brain diseases. So, we want to extract. We are going to scan. We are going to scan brains of different participants so that we generate the brain signal waves from each of the three types or three classes we have. Then each classifier, like I said, distinguishes one class from another. At the prediction time, one classifier gives all classifiers give their outputs, and the class with the highest probability is chosen. Let's say now we have fed brain signal waves to all the three classifiers, and then at the prediction time they all give their outputs. So we choose the classifier with the highest probability. Let's say if classifier 1 has the highest probability, so the new brain signal wave will belong to the Alzheimer's disease or the AD class, because of the highest probability. So this is another example. We have three classes: blue, green, and red, and these are the features and our classes here. So now classifier 1 is classifying or is distinguishing green from the rest. Classifier 2 is distinguishing blue from the rest, and then the third classifier is distinguishing red from the rest. So like how our main data set is this one. So for one now to distinguish green from the rest, so we train we have now our training data set 1. So for each column, or for each class where there is green, we put a positive, and then where there is no green, we put a negative. So after we see that we have two classes of green, and these are the features we have used to train our model to distinguish, to tell between the groups. Now it is basing on these features to tell which one belongs to green. So now we go to the confusion matrix in the 1 versus all setting. So the confusion matrix basically tells how well a model performs in distinguishing each class from the rest. And this is the structure. We have n classes, we have 3 classes, let's say. Then now the confusion matrix will be 3 by 3. Then the rows represent the actual class, and then the columns represent the predicted class. Suppose now we have 10 samples per class. 3 classes have 10 samples, and this is our predicted classes. So for the first one, Alzheimer's disease, which is the AD, have 10 samples. We see that 7 of the samples are predicted to be they are actually predicted true to be Alzheimer's disease, but then the 2 are misinterpreted to be frontotemporal dementia, and then 1 is misinterpreted to be healthy participants. Then like that. Then afterwards we see when we come to evaluate these three, the three classifiers, we see that actually for frontotemporal dementia, it does pretty good, because it has only misinterpreted two instances. No, two samples. So at least the classifier works well with the frontotemporal dementia. Then for one versus all classification, for n class instances in the dataset, we generate the n times, in brackets, n minus 1 divided by 2 binary classifiers. Using this classification approach, we split the primary dataset into one dataset for each class opposite to every other class. This is to illustrate what's in this text. We have our main dataset with the three classes. So we create binary classifiers. Each classifier is using two pairs, and the pairs are different from other classifiers. So the first classifier is distinguishing between Alzheimer's disease and frontotemporal dementia. Then the second one is distinguishing between Alzheimer's disease and the healthy participants. Then the third one is distinguishing frontotemporal dementia from the healthy participants. Then, to understand it very well, this is another example. We have three classes, so we want to find out how many classifier models do we need. We get the theory, then we in brackets we get the 3 minus 1, remain with 2. So 2 divided by 2 we get 1, then times 3 we get 3. So we have 3 binary classifiers here. So for each classifier predicts one class label. So when we input the test data to classify the tested data to the classifier, then the model with the majority counts is concluded as the result. Now let's say we have fed new data to the classifiers. We have fed new maybe brain signal data. So the class, we shall take that. The machine learning model will classify the new brain signal data depending on the majority of the counts from each classifier. Like if this one is from the brain data we have 7 to be Alzheimer's disease, and then 2 to be the frontotemporal, like that. So from all these we take the majority count. The majority count, then if we find that maybe the majority count is Alzheimer's disease, then we shall take the new brain signal wave to belong to Alzheimer's disease class. Yeah, thank you so much for listening. I'll hand over to my colleague to take you through the matrix of 1 versus 1 and other parts of classification.
And you calculate the matrix. So an example of the confusion matrix for the multi-classification is this. So if we have 3 different cases, that is the Alzheimer's disease, the frontotemporal dementia, and the healthy cases. So here you get different classifiers. For this case, still there will be 3 classifiers. And then, for example, if you have to give each pair a class. So if you give the first pair Alzheimer's and frontotemporal, the second pair Alzheimer's and healthy cases, and then the third case you give frontotemporal and the healthy cases. So each classifier has to come out with a prediction. So for this case, In the case of Alzheimer and versus frontotemporal, the classifier predicted that the Alzheimer disease had 7 outcomes, and then the frontotemporal had 3. For this case, for Alzheimer and healthy outcomes, there were 3 Alzheimer cases and 2 healthy ones. So it keeps on going like that. These are the predictions made by the classifiers. But then you have to compare with the actual data. So for this case, since it's a confusion matrix, there will always be the ones that are false or negative and the positive ones. So you have to compare with the actual data to see whether the model is predicting correctly. Yeah, so in confusion matrices, there are true positives, false positives, true negatives, and false negatives. The true positives are the ones where an actual model is predicted correctly, and then like here, A, these are the actual ones, and these are the vertical ones are the actual things, and then these horizontal ones are the predicted ones. So here A was predicted as A here. So this part is the one for the true positive, the ones that were correctly predicted by the model. And then here it's A, but it was predicted as B. So it's a false negative, meaning it has been put among the negatives, yet it's supposed to be a positive, so it's a false negative. And then here B was predicted as A. These are the ones that were predicted as A. So that is a false positive. It was predicted as A, yet it's supposed to be B. So that's a false positive. And then here, these are true negatives. It was predicted as B and it's B. So it's a true one. So these are the methods that they use for calculating the accuracy, precision, the recall, and the inference score. Accuracy, that one, it's like calculating the accuracy of the model. Like how correct is it according to the predictions that it has made. And so each row was representing the actual class, and each column was representing the predictions that the classifiers have made. Yeah, and the final decisions are based on the majority voting across the classifiers. So I'll go ahead with how deep learning is used in multi-class classification. So for our study, we used EEG signals to classify between patients with the different categories of Alzheimer, frontotemporal, and the healthy individuals. So deep learning is it's about neural networks. So for our case, we have 3 classes. So that is obviously multi-classification. It's a multi-class classification problem. So to solve this, we use deep learning, which involves neural networks, because it can detect patterns in the EEG data that are hard to see manually. Yeah, so the deep learning models were developed, or they were built using artificial neural networks. Those were inspired by the human brain, or the human neurons, the neurons in our brains. So it follows that kind of working. Yeah, so in deep learning models, we have the convolutional neural networks. This one, it detects patterns in EEG data like brain waves. Okay, it uses a filter to detect or to check on the differences in signals or patterns. It checks whether there is if a frequency is going higher, if it's going low, it checks for the patterns. It checks for the differences in the frequencies. So yeah, and then there is the long short-term memory network that can track the EEG signals over time to find changes in the brain activity. So this one, it's a kind of recurrent neural network. It works by keeping information of the past signals, and then it uses them to predict the way, like the way the brain will work in the future, or it predicts data, the results of data from the future from the future data that will be input. So it uses the previous data to predict the data that is brought in, the new data. So the advantage of this is that for the EEG data, the brain activities are always changing. So it's good to use the long short-term memory networks, because since they keep track of the previous signals of the brain, they are able to know how the brain is. They learn the pattern. They help the model in learning the pattern of how the brain is working over time. So the brain is always able to predict how the model will perform, or what the output will always be if it has any new data that is brought in. So for deep learning, you first collect the data. For our case, it was Alzheimer for the temporal and the healthy data. Then you clean and process the signals, because that data always has unnecessary things. It has that noise, so you have to remove the noise and then normalize the data. Then you train the model using those two techniques that I've explained before. Then you use the model. You can either, for training the deep learning model, you can either use one or you use both of them, because both of them are good. The CNN will help you for data that has patterns. For the EEG signals have a lot of patterns. They're always changing. So it's good if you use those, because the brain patterns are always changing. They have a lot of patterns and they're always repetitive. Yeah, and then the LSTM, that will help, because the brain activities are always changing. Yeah. So use the model to predict the brain conditions from the new data, and then you check accuracy using the confusion matrix and other matrices. Yeah, as I showed you before, the methods that we use for calculating the accuracy, the precision, the F1 score, use all of those to calculate the results from the model. And then the challenges that we face during multi-class classification, there is class imbalance. So this happens when different classes have different numbers of samples. But then there are some classes that may have a very high number of samples, and then the others may have a very low. For example, if there are like 3 classes, and the model is supposed to use those 3 classes to learn, or for the training, the model may get biased if it's over working on the class that has the highest number of. Here you can create duplicate data in the classes that have little samples. So it will kind of balance the samples between the classes. And then weighted loss functions. There you add weights to the classes. So that's the classes that have little samples may be seen by the model as though they are like very important. So it will give them a lot of attention. And then feature complexity. Here, signals contain a lot of noise and unneeded things. Yeah, they have high dimensionality, so it can cause like a lot of unnecessary things. Like the model may end up having to go through unnecessary data, because there is a lot of unnecessary data that is in the EEG signals. So the solution is feature selection. You can select only the most important data, or dimensionality reduction. You remove the ones that are not so important. So that will ease the work of the model. And then overfitting, yes, because EEG data has a little, may have a lot of unnecessary information, so the model may end up learning or trying to memorize the training data instead of actually learning the patterns. So a solution to that is using dropout. So here you can randomly turn off some neurons so that the model can learn how to find its own pattern without following the path that you set for it. Because if it's like, if I can give an example of like teaching a student, if you've given a student a certain textbook and then you take it away from them all of a sudden, they'll have to look for a different way to study, or a different access to the notes. So that's how the model will be. If you just turn off some neurons at some point randomly, it will have to look for another pattern. Then regularization. There the model will have to the sorry about that. So for regularization, there is a lot of complex things. There are a lot of complex things in the data. So the model will have to focus on the most important parts, because if you can, okay, since the EEG signals have a lot of noise, a lot of unnecessary data, it the data may end up picking some features that it's going to concentrate on. So you can decide to penalize the model if it's concentrating on those certain features. So there it will be forced to work on all the features. It will be forced to work on the features like on the different weights. Yeah, and then there is cross validation. So instead of training the model on the whole dataset at once, you can decide to split it into different sets. So it will have to memorize all the different sets, since it's been broken down into smaller parts. It will memorize them easily, or it will learn the patterns easily. Okay, so here is a simple example of multi-class classification. So for our code here, we first load the data set. We use the iris data set. It loads the data set, and then for the x here, the x is for the features. The features, like, okay, this data set it has 3 classes. There are 3 different flowers that it's supposed to classify. So the x's are for the features, maybe the petal length or the colors of the flowers. And then the y, those are the actual labels, like the actual names of the flowers. So the data set is split into 2, the training and the testing data set. 80% is for training and 20% is for testing. Then it's trained using the logistic regression. Then the data makes the model makes predictions. Then it prints out a classification report and a confusion matrix. Then it plots a graph that shows the results from the confusion matrix. Yeah, it also prints out the predicted values and the actual ones. Yeah, so these are the results from the implemented code. The classification report these are the 3 flowers. The classification report these are the 3 flowers or the classes, and the precision results, the recall F1 score, and the support. So this structure has precision of 1, recall of 1, that means our name is classifications. Then the vesicular has 1 precision and recall it has 0.89. That means a certain percentage was misclassified. Same applies to vaginica. The precision is 0.92 and then the recall is 1. So that means some part of it was misclassified. So this is our graph. Here we also calculate the accuracy, the macro average, and the weighted average. I gave the formulas in the previous slides. So this is our graph. The diagonal pattern shows the classes that were correctly classified, and then the color of blue, or this dark blue, shows the ones that have the highest number of features. These parts that are very faded blue are the features that were misclassified, and then these ones were the ones that were correctly classified. The horizontal line is for the predicted outcomes, and these are the actual ones. So yeah, that was all I had for you. Thank you very much.